All right, in 4.1, we are going to take a look at exponential functions. So first, our definition of an exponential function is just any function where a variable is in the exponent. So our basic standard exponential function is just some number raised to the x power. Now, the number is called the base, right? This is called the base. And now we're saying the base has to be a positive number, and it can also not be 1, because any number, if the base were 1, right, 1 to any power is just 1. So real quick, let's just take a look at evaluating some exponential functions. So f of 5 in this case means I'm plugging 5 in place of x. So f of 5 would be 3 to the 5 minus 2 power, which would be 3 to the third power. And 3 to the third power is 3 times 3 times 3, which would be 27. Then this one, the negative second power, right? So g of negative 2. So I've got a negative 2 out front, right? But remember, in order of operations, we have to do exponents first. So I would raise 10 to the negative second power first. Now, another thing that we have to remember in this case is how to treat negative exponents. So a negative exponent just means take that to the denominator and make the exponent positive. So 10 to the negative second power is the same as 1 over 10 to the positive second power. And 10 to the second power would be 100. So this would be 1 over 100. And then finally, I can multiply by that negative 2. So this would become negative 2 over 100. And we can actually reduce that to make that just negative 1 over 50. And our final example, we've got f of 3.2. So we can have powers that aren't whole numbers, right? So 4 to the 3.2 power. We'll have to use a calculator for that, right? So if we bring up a calculator, 4 to the 3.2 power would be 84.449. Generally, when we're looking at exponentials and logarithms later on in this chapter, we'll go to 3 decimal points. So if I round this to 3 decimal points, that would be 84.449. All right, so let's then review the rules of exponents. Okay, that's going to be important when we're talking about exponential functions. So here, if I have some number to an exponent times that same number to a different exponent, to combine those into the same term, I would just add the exponents together. For example, if I had x to the fourth power times x to the third power, that would just be equal to x to the seventh power. Now, all of these rules only work if we're talking about the same base, right? If this were x to the fourth times y to the third, I would not be able to combine them like this, right? Now, if I'm dividing, I subtract the exponents. So if this were x to the sixth over x to the fourth power, I would just subtract the exponents, and this would be x to the second. Right? I'm sure that you've all seen the reasoning behind this. If we were to write this out, this would be x times x times x times x times x times x over x times x times x times x. And we could cancel out 4 of those pairs of x's, and we would just be left with x times x in the numerator. That's where this rule comes from. Then any number to the 0 power is equal to 1. Right? So 17 to the 0 power is equal to 1. Anything to the 0 power is equal to 1. Our next rule is how to treat negative exponents. Right? Any number with a negative exponent, that would be the same as taking that value to the denominator. So if I have 4 to the negative second power, well, that's the same as 1 over 4 to the second power. Now, we could also say, if we have 1 over 5 to the negative third power, I could bring that to the numerator and make that a positive power, right? It works both ways, okay? Then we have a power to a power, right? If I'm raising a power to a power, I multiply them together. For example, if we have x to the third to the 5th power, this would be x to the 15th power, because this would be x to the third multiplied out 5 times. And our final rule is if I have 2 things being multiplied or 2 things being divided and that whole thing being raised to a power, then I can just essentially distribute the power to both of those. So an example of that would be, if we've got xy to the second power, this would just be x squared times y squared. Or if I've got x over y to the third power, that would just be x to the third over y to the third. Now, note this does not work if I'm adding or subtracting, right? This only works because this would be xy times xy. If I've got, x plus y to the second power, remember that's where we have to multiply this out. X plus y times x plus y. So this idea of essentially distributing an exponent only works if those terms on the inside are being multiplied or divided, not if I'm adding, right? So this idea does not work if I'm adding or subtracting. So let's look at a few examples using those rules. So here, I do have the same base if I'm multiplying these together, so I can just add the exponents. Now, this problem actually brings in another element. I cannot just add the square root of 8 and the square root of 2. I need to simplify the square root of 8 first. So let me come off to the side here. Let's say the square root of 8. If I want to simplify that, I'm looking for the largest perfect square that divides evenly into that. Well, I can make this the square root of 4 times the square root of 2. And then the square root of 4 is just 2. So the square root of 8 is equal to 2 times the square root of 2. Whenever I want to add or subtract radicals, I need to have the exact same thing on the inside of the radical. So this would be the same as 3 to the 2 radical 2 power times 3 to the square root of 2. Now, if I add the exponents, I'll have 3 to the 2 square root of 2 plus 1 square root of 2. And these then I can treat like terms. 2 square root of 2 plus 1 square root of 2 would be 3 square root of 2. Okay? Let's try another one. So here I've got a power to a power. Whenever I'm multiplying radicals, I can multiply what's on the inside. So this one's a little bit easier, right? This one would just become c to the square root of 21. I can't simplify the square root of 21 at all, so that would be my final answer in this case. Now this one, I do not have like bases. In order to use any of these rules, I have to have the same base. So I need to try to rewrite these with the same base. Both 9 and 27 are powers of 3. Okay? As we get further into this chapter, we're going to need to recognize things like that. So I could actually rewrite this as 3 squared to the square root of 5. Right? I just replaced 9 with 3 squared. And 27, I can rewrite as 3 to the third power. And that would be to the 2 square root of 5. Now I've got a power to a power in each of these. I can rewrite this as, if I multiply these together, 2 times the square root of 5. And in the denominator, if I multiply these together, I could rewrite that as 3 to the 6 times the square root of 5 power. Now, since I'm dividing, I can subtract my exponents. So 2 square root of 5 minus 6 square root of 5 would be negative 4 square root of 5. But generally, we don't want to leave our answers with negative exponents, so I can then rewrite this as 1 over 3 to the 4 square root of 5 power. All right. So now let's talk about graphing exponential functions. Okay, so let's start by just creating a table of values for a couple of problems. Okay, so plug in x's, y's. So let's plug in -2, -1, 0, 1, and 2. So if I plug -2 in, 2 to the negative second power, well, we just talked about what that means. That means 1 over 2 to the second power, and 1 over 2 to the second power would be 1/4. So the point -2, 1/4 is on my graph. If I plug -1 in, 2 to the negative first would be 1 over 2 to the first, or 1/2. So the point -1, 1/2 is on my graph. If I plug in 0, again, we just talked about this property, any number to the 0 power is equal to 1. So the point 0, 1 is on my graph. If I plug in 1, 2 to the first is just 2. So the point 1, 2 is on my graph. And finally, if I plug 2 in, 2 to the second power would be 4. So the point 2, 4 is on my graph. And we can see this function that we are creating here. Now, this function is actually going to have an asymptote at y equals 0 at the x-axis. This graph is never going to cross the x-axis. Okay, so this is what a basic exponential function would look like. Okay, so now let's try the same thing, but with y equals 1/2 x. Okay, so again, let's plug in those same values, -2, -1, 0, 1, and 2. So if I plug in -2, 1/2 to the negative second power, well, I could distribute that negative second power into both of those, right? And this would be 1 to the negative second power over 2 to the negative second power, which I could just rewrite, making those exponents positive. I could rewrite that as 2 to the second power over 1 to the second power, which would be 4 over 1. So the point -2, 4 is on this graph. Same idea here, right? If I do 1/2 to the negative first power, distribute that in, and then flip, this would end up being 2 over 1. So the point -1, 2 is on the graph. Then 1/2 to the 0 power, well, anything to the 0 power is equal to 1. So the point 0, 1 is on the graph. Then if I plug in 1/2 to the first power is just going to be 1/2. And finally, if I plug 2 in, I'll have 1/2 to the second. So this would end up being 1 squared over 2 squared, which would be 1/4. So the point 2, 1/4 is on the graph. So we actually end up seeing something kind of similar to what we just graphed. If I can connect my dots here. Okay. This ends up actually just being what we just graphed reflected across the y-axis. The reason for that is I can rewrite 1/2 as 2 to the negative first power, and then multiplying those exponents together, this would just be the same as 2 to the negative x power. Okay? Now, let's take a look at some properties of exponential functions and then also graphing them. So, if we have our exponential function with some positive base not equal to 0 or not equal to 1, that should actually say not equal to 1. Now, note some of these properties are different if we shift the graph at all, and we'll talk about shifting here in a second. But the domain of any exponential function is all real numbers. The range is just 0 to infinity. Now again, we could shift the graph and our asymptote would change, but the range is 0 to infinity. If my base is greater than 1, the function is increasing. If the base is in between 0 and 1, my function is decreasing. And we just looked at 2 examples of that, right? For this one, the base is greater than 1, my function is increasing. For this one, my base was in between 0 and 1. The function is decreasing, right? Now, each exponential function is 1-to-1, which means exponential functions have inverses, and we'll look at that in a later section. There are no x-intercepts because that line y equals 0 was an asymptote. The function is smooth and continuous and passes through these 3 points. Right? Remember what we just looked at. If we plugged in -1, we got 1 over whatever the base was. It always went through 0, 1, and then 1, whatever the base is. Now again, note those could be different if my function is shifted at all. Y equals 0 is a horizontal asymptote, and like we just mentioned, the graph of a to the negative x is the reflection of y equals a to the positive x across the y-axis. So if you remember back in the previous section when we talked about shifting functions, right? If we had these 4 different shifts, a, if we had a value out in front, that was a vertical stretch or compression. B was a horizontal stretch or compression, C was a horizontal shift, and D was a vertical shift. So we can have the same thing with exponential functions. A value out in front would be a vertical stretch or compression. Now, notice here, since x is in the exponent, then my b and c values would also be in the exponent if I have those shifts. So a b value would be a horizontal stretch or compression, a c value would be a shift left or right, and a d value would be a shift up or down. So let's take a look at some examples. Now, if we think about this 5 to the negative x, this would be the same as if I start with 5 to the positive x, and this negative sign, this is like being on the inside of the function. So we said a negative on the inside was a reflection across the x-axis. So I'm going to take 5 to the x and reflect across the x-axis. So 5 to the x, right, would, I guess my axis should be up a little bit to make this a decent graph, but 5 to the x, I'll draw that first, right, would do something like this. It'd be a pretty steep curve. So again, I'm graphing 5 to the x, not 5 to the negative x. So 5 to the negative x then would be this graph reflected across the x-axis. So that would end up being here and would go real steep here. I should have put my axes up a little further. Right? So 5 to the negative x would look something like that. Negative 3 to the x hold up, I messed that up, didn't I? Apologize. So here's my 5 to the x. 5 to the negative x, if the negative is on the inside of the function or with the x, that is a reflection across the y-axis. So 5 to the negative x would look like this. There we go. All right, so now in this one, negative 3 to the x, this is what we were just talking about. I guess I should change this as well, reflection across y. So here, if my negative sign is out front, that's when we are reflecting across the x-axis. So here, if I'm taking 3 to the x, I would be reflecting this across the x-axis. So 3 to the x, let me graph this one first, would go through the point negative 1, 1/3, 0, 1, and 1, 3. So now if I take that and reflect across the x-axis, here is negative 3 to the x. Okay? And then our final example here, if I've got 4 to the x, and I've got a c and a d value here, I would be shifting 4 to the x right 3. Remember, we take the opposite value here. So I would be taking 4 to the x and going right 3, and then up 1. So let me graph 4 to the x first. I would have -1, 1/4, 0, 1, and 1, 4. So here's my 4 to the x, and I'm going to take this and go right 3, up 1. So let me just take each of those points that I have already. So I'm going to take this point and go right 1, 2, 3, up 1. Take this, go right 1, 2, 3, up 1. Then I can take this one, right 1, 2, 3, up 1. So here is where this graph will be. Now also notice that my asymptote is going to be shifted up 1. Since my asymptote before any shifts is y equals 0, since I shifted up 1, my asymptote now is going to be y equals 1. So my graph is going to get closer and closer to y equals 1, but never touch it. Okay? So let's now talk about this example problem. We want to find an exponential function that goes through these 2 points. Okay? And they tell us it's going to be in this form, y equals some number times a to the x. To do a problem like this, I'm going to plug each of these points into my function separately for x and y. So if I plug 12 in for y, equals c times a to the first, and then I'm going to take this point and plug it in separately. So I'm going to plug in 108 for y equals c times a to the third power. Now what I'm going to do is solve both of these for c. So what that means is I'm just going to divide both sides by a to the first in this case, and both sides by a cubed in this case. So I guess I can just rewrite that here as 12 over a equals c. And then here I'll have 108 over a to the third power equals c. Now, since I solved both of these for c, I can say they are equal to each other. Okay, if they're both equal to c, then they're equal to each other. So what I can do now is say 12 over a equals 108 over a cubed. And I can just cross multiply and solve now. So if I cross multiply, I'll have 12a cubed equals 108a. So now I just want to get my a's on one side and my numbers on the other. So I'll start by dividing both sides by a. If I divide this side by a cubed over a would just be a squared. And then I'll divide both sides by 12 to get the variable by itself. So 108 divided by 12 is 9. And now I can just take the square root. Now, we are not going to take the positive and negative root here because we are solving for the base of an exponential. And we said the base of an exponential has to be positive. So my a value is 3. I still need to solve for c though. To do that, I can take this value and plug it back into either of my equations. This one will probably be the easiest. So if I plug that in there, I'll have 12 over 3 equals c, and 12 over 3 is just 4. So, oops. My final answer then, taking these two values and writing a function, is going to be y equals 4, which is my c value, times 3, which is my a value, to the x. Okay, so that's my final answer, that function. This graph would include both of those points in an exponential form. All right, so let's talk about interest now. Okay, first, simple interest. Simple interest is basically where you would not earn interest on your interest. You only earn interest on whatever amount you invested. So the simple interest formula is I equals PRT. So I stands for interest. The P stands for principal. Principal is the amount that you start with. R is the rate. And T is time. Okay, so let's take a look at a simple example here. Let's say Alex invests $1,000 at 7% per year. So to write this information in our equation, we're going to say I, the interest, is equal to the principal amount, which would be 1,000 in this case, times the rate. Now we want to write the rate as a decimal. So 7% as a decimal would be 0.07. And then times time, which is the number of years. So here, for part B, I want to find after 1 year how much interest. So I'm just going to plug 1 into this function. So this will be 1,000 times 0.07 times 1. Okay, so we could plug that into a calculator, but probably don't need a calculator for that. Right? That's going to get me 70. 1,000 times 0.07 times 1. Do the same thing for 5, right? So 1,000. I guess we should emphasize that this is the amount of interest. Okay, so after 1 year, $70 in interest. After 5 years, do the same thing, right? And hopefully this makes sense that after 5 years, 1,000 times 0.07 times 5, well, it's just going to be this amount times 5. So this is going to end up being 350. Now, the total amount then would be what he started with plus the interest. So after 5 years, he's going to have $1,350, right? This is just the interest that he's earned on the account. So the total after 5 years is 1,350. Okay? Now, simple interest is not usually how banks or any financial institutions do interest. Usually, they compound the interest. You can earn interest on your interest. Okay? This is our formula for compound interest. Okay? Now, this formula, this A stands for the amount or the final amount in your account. This is not just the interest. This is the total amount in the account. P is, again, the principal. This is what we're starting with. Now, R is again the rate. N actually shows up twice in this formula. This is the number of times we're compounding per year. Number of times compounding per year. And then T, time, is the number of years. Okay? So let's take a look at how we use this formula. So in our example here, we've got $2,200 deposited into a bank that pays 5% interest. We want to find the future value after 2 years. So 2 is my T, my number of years, if the interest is compounded a few different ways. So annually means once a year. So in this case, I'm going to put 1 in for n into my formula. So let's write this whole thing out. So we will have my A, which is what I'm solving for here, equals 2,200. That's my principal amount, times 1 plus my rate, which is 5%. Remember, we have to write that as a decimal. 5% would be 0.05 over the number of times per year, which is 1, to the number of times per year times the number of years. So here is what I'm going to plug into the calculator. Okay, and we can absolutely use our calculator here. So let's bring that up. So 2,200 times 1 plus 0.05 over 1. And we wouldn't have to put it over 1 in this case. To the 1 times 2 power. And we get 2,425.50. So we've gained a little bit of interest here. Okay. Now let's see how that would change if the only thing I change is compounding semi-annually. Semi-annually means 2 times per year. So I'm going to take all the same information and plug into this formula. The only thing I'm going to change is I'm going to make this n value 2. So this is going to be 2,200 times 1 plus 0.05 over 2 to the 2 times 2 power. Okay, so let's plug that into the calculator. All right, and I'm going to use my second entry feature here and just change these values. It should save me a second of time. And let's see what we get. So we get a little bit more money, right? Like a little less than $3 more, right? So 242839. Okay. Let's do the same thing now for quarterly. Quarterly is going to mean 4 times per year. Okay, so again, same formula. The only thing I'm changing now is I'm putting in 4 for my n. So 4 times 2. So again, plug that into the calculator. If I hit second entry, I can just change these values to 4s, and we get a little bit more money, right? So 2429.87. Now, I guess I should mention compounding just means this is when they're calculating the interest, right? So if we do it once a year, twice a year, 4 times a year, right? Let's do it monthly, right? Well, every month would be 12 times per year, right? So I'm plugging in 12 for n. Again, same formula. So 2200 times 1 plus 0.05 over 12 to the 12 times 2 power. So plug that in the calculator. Second entry, just putting 12 in here. And whoops, I messed that up, didn't I? Got rid of my multiplication sign. So let's fix that. That should be times 2. There we go. So 2,430.87. So we keep getting a little bit more money as we compound more often. Not a lot, but a little bit. Let's do one more here. Let's do daily. What if they compounded every single day? Well, that would be 365 times for the year, right? So we're using the same formula, same information, just plugging in 365 for n now. So a equals 2200 times 1 plus 0.05 over 365 to the 365th times 2 power. So plug that in. Let's do second entry. 365 times 2. And replace this one with 365. And we'll get 2,431.36. So every time we increased the number of times we were compounding, we got a little bit more money. All right, next, let's take a look at an example of solving for a piece of information using this formula. So here it says, how much would you need to invest if you want to have $1 million by the time you retire in 35 years. Assume that interest is 6% compounded monthly. So we want to start with our formula. A equals P times 1 plus R over N to the NT power. And let's take a look at the information that we have. We know, let's see, that the rate is 0.06. I know that my time in years is 35. So T is 35. And I know that this is compounded monthly. So that means that my N value, the number of times per year that this is compounded, is 12. And now this $1 million, that's what I want my final amount to be. That's what my A is going to be. So in this case, I'm solving for P, the principal amount. So what I want to do is plug all of this information in. So I want to say 1 million equals P times 1 plus R over N. Whoops, that should be 12 to the NT power. So 12 times 35 power. Now, to solve for P, I'm just going to divide both sides by this whole thing here. Now, to get an exact answer, I'm just going to put all of this into the calculator. All right, so I'm going to do 1 million, and I'm going to put this as a fraction so that we can see a little better. So 1 million divided by 1 plus, put in another fraction here, my 0.06 over 12 to the, what did we have? 12 times 35. And I get that my principal amount, the amount that I would need to invest, would be $123,098.87. Okay, so I mean, this isn't super realistic because you would continue to invest money as you have it. But if you were able to invest $123,000 35 years before you retire and get a 6% interest rate, you'd have $1 million by the time you're retired. Okay, so the final part of this lesson is to look at the number E. Okay, it's called the natural number or Euler's number. This name, Leonard Euler. Okay, it's not Euler. This is pronounced Euler. He was a famous mathematician. So if we look back to our examples here, where we were, compounding the same amount of money annually, semi-annually, monthly, daily, right? We continue to get a little bit more every time. So what we want to start to think about is, well, if we continue to increase this, if I compound it twice a day or 10 times a day or 100 times a day, will this continue to increase without bound? So let's do a little experiment to figure that out. Let's start with our compound interest formula here. And what I'm actually going to do, right, is rewrite this just a little bit. So I'm going to change this exponent nt. I'm going to divide it by r and multiply it by r. Okay, multiplying and dividing by the same thing wouldn't change the value. So that's how we got from this step to this step. I wrote nt as n over r times r to the t power. And again, this isn't going to be immediately obvious why we do this, but I'm going to explain it here in a second. And then I'm just going to rewrite that n over r as h. So if I do that, then r over n would be the reciprocal of n over r, so that would just be 1 over h to the h power. So what I'm going to do is just take a look at this piece right here, this 1 plus 1 over h to the h power. Right? This is kind of like this factor here that we're raising to a power. So I want to see what happens as I plug in a larger and larger h, right? H is like the number of times I'm compounding per year. So if I start plugging in values of h, let's just start with 1, right? If we compound it once a year, all right, so we plug that in the calculator. That's pretty easy. That just becomes 1 plus 1 to the first power. So 1 plus 1 is 2 to the first power. All right, so let's plug in 2. All right, if I plug in 2, then I get 1.5 squared is 2.25. All right, so that factor is increasing. Well, let's plug in 10. Okay, if I plug in 10, I get 2.59374. So that number, keeps going up. Let's plug in 100. Okay, say we're compounding 100 times per year. See what this factor ends up being. Well, 2.7, right? So we keep increasing. Right? Let's go even bigger. Let's plug in 1,000. Okay, so if I plug 1,000 into this, right, say we're compounding 1,000 times per year. Well, that didn't go up that much. We went from 2.70 to 2.717. Okay, so we're going up still, but not by as much. Let's go to 10,000. Let's say we're going to compound our interest 10,000 times a year. Let's see what this factor of 1 plus 1 over the number of times to the number of times power ends up being. Wow, that didn't go up by much at all. 2.718. Right, yeah, hardly increased at all. Let's say we want to compound 100,000 times. Right, let's plug that in the calculator. Wow, that hardly increased at all. 2.71827. Okay, let's do one more. Let's do 1,000,000. Let's say we want to compound our interest 1,000,000 times a year. Plug that in. Again, that hardly increased that factor at all. Right, 2.71828. Okay. what actually happens is this value here, this 1 plus 1 over h to the h power, this approaches a finite value. Okay. That finite value is the number e, and it is an irrational number, just like pi. Okay? But here is the value of e to 15 decimal places: 2.718281828459045. It almost looks like it's going to start repeating here, but then it doesn't. It is an irrational number. Now, to give you a little bit of calculus notation here, this we can write as what's called a limit. All right, so if I take that 1 plus 1 over h to the h power that we were just talking about, this is essentially that factor of what's happening when we compound a certain number of times per year. If we make h really large, if we say as h approaches infinity, we say this is equal to that number e. Okay, so this is some calculus notation, a limit. Right? So we're saying as this variable, as h gets really, really large, as it approaches infinity, we get closer and closer to this value of e. Right? Now, e actually ends up being really useful in lots of real-world applications, and we'll take a look at a few of those throughout this chapter. Okay, and it's so important, there is actually a button on your calculator dedicated to the number e. So on your calculator, right above the division sign, you see a blue lowercase e. If you hit the second button and then the division button, you will get the number e on your calculator. Okay, and we will use that throughout this chapter. So the final example here is just the continuously compounded interest formula. So don't write this one down, okay? what we're saying is if I take that formula, that we just had, the principal times and what we did that little substitution, this 1 plus 1 over h to the h power, we're saying that's just equal to e. So if we are told that interest is continuously compounded, right, that means we're compounding it essentially an infinite number of times, right? It's just constantly compounded, not once a day or once a week, right? We're compounding it continuously. This is our formula to calculate the amount. It's the principal times the number e raised to the rate times time power. So in our example here, we want to start with a principal of 8,300, invest it at a 7.5% interest rate, compounded continuously for 8 years and 3 months. So we're starting with this formula. A equals P times E to the RT power. So in this case, I know that my principal amount is 8,300 times E to the rate, so 7.5% as a decimal would be 0.075 times time, and time is in years. But here I'm told we want 8 years and 3 months. I want to somehow write 8 years and 3 months as a decimal. So what we want to think about is 3 months would be 3 out of 12, right? 3/12ths of a year. So 3/12ths as a decimal would be 0.25. So 8 years and 3 months would be 8.25 years, okay? So that is the value that we want to plug in for the time, for the number of years, 8.25. And then we can plug all of this into the calculator. So we will have 8,300 times E raised to the 0.075 times 8.25 power. And we get $15,409.83. Okay. All right. So that is it for this video. The homework assignment is slightly longer as well, so it might be a good idea to work on that before we get back into class. The final question is going to pop up asking you what questions you have.